Today we're going to look at reduction potentials and how they vary with ligand and environment effects such as solvent. So if you were to look at a table of standard reduction potentials, you find a reduction potential for ferric ion or cupric ion. And if you then looked at other examples that contain ferric or cupric ion, you might find reduction potentials that are very different. So for instance, just to pick a couple of examples, because there are lots of them, in biochemistry, cytochrome C, there are lots of different cytochromes. Cytochrome C contains iron 3+, a ferric ion, and it's got a reduction potential that's much, much lower than what you would see in a standard table of reduction potentials for iron 3+. And similarly, lactase, fungal lactase, is a copper-containing enzyme that has a reduction potential that is much, much higher than what you'd see for copper in a table of reduction potentials. So reduction potentials can vary depending on the environment of the metal. And this is not just a biology versus chemistry thing or something. If you look at other inorganic iron salts, such as ferrocyanide salt, that reduction potential is very different than the one you see in the table as well. So why is that? And one of the things I should point out right away is that when you look at this result in a standard reduction potential table, these things are really aqueous. They're measured in water. And so for instance, in the case of the iron, what we're really dealing with is the reduction potential of the iron ion that's ligated by water. So it's probably a hexa-aqua complex gaining an electron. And we're really comparing that, for instance, to the iron in the hexacyano complex, which is a 3- overall charge and all these different ligands. They're not waters, they're cyanides. Versus the cytochrome, and cytochrome has a heme ligand. So just to do a quick cartoon of the heme ligand, the iron is ligated by two formally anionic nitrogens and two formally neutral nitrogens. And so overall, the charge here is 0. But we've got ligation by oxygen, by nitrogen, by carbon here. Now we've got different charges on the complexes, and all of these things can play a big role in tuning the reduction potential. So let's take a look at some of these factors. And by the way, you're not going to get to a point where you'll be able to look at a complex and predict its reduction potential or anything like that. That's too complicated for that. But you will get to a point where you can look at two complexes and you can look at their two reduction potentials, and you may be able to propose a rational explanation for the difference. So the first thing we're looking at is ligand effects, because the ligand is directly attached to that metal that's gaining the electron. And so it should have a pretty pronounced effect. And one thing you can change in ligands is you can change the charge. So for instance, if we're thinking about these biochemical examples still, we might have a cysteine, where it's a sulfur ligand, versus a methionine, where it's also a sulfur ligand, but the sulfur is anionic versus neutral, okay? Now that's going to make a difference because we're donating a different amount of electron density to the metal. This one's anionic, this one's neutral. And so this one's going to give more electron density to the metal compared to this one. But that's not all. We have a charged ligand here. We might have a charged metal. And so what we're also doing is changing the overall charge on the complex. Maybe this is still +2 and this is +1. And that charge on the complex is going to influence its reduction potential. And what's specifically going to be important about that charge is the change in charge. When we go from here, adding an electron, does the complex become more charged or less charged? And as I've drawn that example, it would become less charged as we reduce it, for instance. So there are a lot of things to balance here when we're thinking about the charge and the ligand. Now, you've also learned before about types of ligand donors. And so I say donating versus withdrawing effects, and it sounds a little silly to talk about a ligand as having a withdrawing effect, but of course, there are sigma donors and pi donors that simply and solely donate electron density to the metal, but there are also pi acceptors, things like that cyanide that we saw in the other slide. That's a pi acceptor, and so it's donating through its sigma bond, but there's also pi acceptance into the pi system. So different ligands may donate and withdraw to different extents, and that's going to change the amount of electrophilicity, essentially, of the metal. And there could be inductive withdrawing effects too. So you might have a ligand that's donating through one atom, and then a few atoms away, you've got something else that's withdrawing electronegativity. And so this is one of the reasons why amino acid side chains can have different acidities, for instance, depending on how far away they are from other electronegative groups. Well, it's a similar idea. The amount of electron donation from this ligand depends on other factors further away. And you can even have hard-soft effects. So if you have a cysteine like we had up there, but in another case you had a serine, well, those two things look an awful lot alike. We're just changing out an oxygen for a sulfur, so we're getting harder. And sometimes that will stabilize a higher charge on the metal, for instance. Right? So there are a lot of things that can vary in the ligands that might influence the reduction potential. Let's step one step further out, away from the coordination sphere of the complex, and think about the solvent or other environmental effects. And just like we've talked about, the overall charge on the complex is important, and the change in that overall charge as you go from reduced state to oxidized state, or vice versa. The charge stabilization is really important, and solvent polarity can play a big role there. So obviously, a more polar solvent is going to better stabilize the more charged complexes, okay? And what sort of an influence will that have? All right. Similarly, hydrogen bonding can play a role. And in this case, if you've got a ligand that's bonding to the metal, but it's got another lone pair on it, and that's donating to a hydrogen bond, that hydrogen bond is actually pulling electron density away from that ligand. And so the lone pair that's supposed to be donating to the metal may be less available because of this sort of competing effect here. So that might increase the reduction potential on the metal because it feels less electron density around it. Now, conversely, covalency of a coordination complex can change with solvent polarity. So increasing solvent polarity increases the ionic character of a complex. So you can go from something in a non-polar solvent that's very tightly bound to something in a more polar solvent that is a little bit more loosely bound. And these charges on the ligand and the metal tend to increase a little bit in those polar solvents because it's stabilizing those charges a little bit more. And so you can have cases where in a more polar solvent, the reduction potential goes up simply because the metal ion is more exposed, okay? And a very closely related idea is that sometimes you can have geometric distortions going on where you've got something that's maybe for coordinate, but if one of the ligands pulls away from the metal, it starts to look more 3-coordinate. And if it's more 3-coordinate, there's less electron density at the metal. And so maybe, again, the reduction potential of the metal goes up because of that ligand being too far away. Right? So these are all kinds of effects that you can see in different cases. And your goal is to just look at what differences you can spot between different pairs of complexes and see whether you can identify what is the origin of that difference based on these effects.